So today we are going to solve from the year 2020, and in this we are going to provide the solution for the 15 questions, and all these questions are from mains, and this is the part 1 for the year 2020. First question, it states that effective capacitance of parallel combination of two capacitors C1 and C2 is 10 microfarad. When these capacitors are individually connected to a voltage source of 1 volt, the energy stored in the capacitor C2 is 4 times that of C1. If these capacitors are connected in series, their effective capacitance will be. So we are given two capacitors which are in parallel combination. The equivalent capacitance is there 10 microfarad. So we start from there and we say effective capacitance in parallel. So we can write C1 plus C2 is our 10 microfarad, and the relationship between the energy is given. So we know that energy stored in the capacitor capacitor, if we given as U, is equal to our half CV square, and both are connected to the same voltage source, that is 1 volt, and the relationship between the voltage is given as if C2 capacitor is having a voltage of U2 and C1 is having a not voltage but energy of U2 and C1 is having energy of U1. Therefore we are given that our U2 is equal to 4 times U1, and we can easily substitute it. So the first U2, we get this as our half C2 V square, because voltage source is same for both capacitors, and half C1 V square multiplied by 4. So here this half voltage and voltage goes away, and we get from here that our C2 is equal to 4 times C1. And we can use the relationship of C2 and C1 and easily find out using equation 1. So we say from equation 1, which is given as C1 plus C2 is equal to 10 microfarad, we substitute C2 is equal to 4 C1. This gives us C1 plus 4 C1 is equal to 10. This gives us that our value of C1 is equal to 2 microfarad. And from here we can say our C2 is 4 times C1. So this comes as 4 multiplied by 2 microfarad, giving us 8 microfarad. So we got the value of C1 and C2. So we have to find out the equivalent when they are connected in series. So we can say effective capacitance in series let us call this as CS. So we can write 1 upon CS is equal to 1 upon C1 plus 1 upon C2. This comes as 1 upon 2 plus 1 upon 8, and 8 will be a LCM. This comes as 4 plus 1, that is 5. So we can write that equivalence capacitance of CS will be equal to 8 upon 5, and which approximately is equal to 1.6 microfarad. So option 3 is correct. Option 3 is correct. Next question. We are given a capacitor is made of 2 square plates, each of side A, making a very small angle. Here angle should be actually alpha, because in the figure it is given as alpha. Okay. Between them, as shown in the figure, the capacitance will be close to. So basic figure is given to us, and we are given a parallel plate capacitor, and the distance between them is given as D, and one of the plate is making an angle of alpha with the horizontal. Okay. So in this case we have to find the capacitance. So obviously the capacitance is going to vary, and let us assume that this initial point is our x equal to 0, and this final point is our x is equal to a, and here in between we are going to consider a thin whose thickness is suppose dx, and it is at a distance of x from the origin, and its thickness is given as dx. So its height on the one part will be d, and on the other part will be our x times alpha, because this x will be same here. So therefore we considered that at any point x, along the plate, the gap between the plates we can approximately, okay, we can write just an approximation for that, and let us suppose that distance between a plate is dependent upon the x. So we write d of x will be approximately equal to over d naught plus x multiplied by tangent of alpha, and we can further approximate it as d naught plus x times alpha. This is under the condition that this alpha is very much less than 1. d naught is a variable which is somewhat, you can say, same as that of a distance d. And if we put x equal to 0 in this equation, so we can say for x is equal to 0, then our d naught is our minimum separation between the plates, minimum separation. And we can say this minimum separation will be nothing at value of d, okay, because the minimum separation is at x equal to 0, okay, and this minimum separation is given as d. Okay. Now we considered a, you can say, small vertical strip of width dx. Considering a small vertical strip of width dx, and here our, one second, okay, so this is our a small strip which we have considered at a distance x from the origin, and therefore we can write that our plate area, therefore we can say that our each strip acts as a parallel plate capacitor, parallel plate capacitor. Therefore we can say our plate area will be equal to a times dx, and separation between the plates which is our d of x will be equal to our d naught plus x times alpha. Therefore for this small strip we can write the capacitance, therefore we can say capacitance, which is our small capacitance dc, will be equal to epsilon naught multiplied by area, which is a times dx, and separation between the plates, which is our d naught plus x times alpha. And for the entire plate, the capacitance if given as C, then we can write this capacitance C will be equal to integration of from x is equal to 0 to a dc. We substitute value of dc is 0 to a, this comes as epsilon naught a divided by d naught x times alpha, and this is our dx. So we are only interested epsilon naught A we can take as common, and this can be written as epsilon naught A 0 to A, and we have dx, and this is our d naught plus x time alpha. Here d naught and this x plus alpha will be our constant, therefore we can, or let us do it more traditional way, and we substitute that our d naught plus x alpha is supposed as u, so we can say our du will be equal to alpha times dx, or we can say our dx is equal to du divided by alpha, and we need to find out the limits. So we say that our x is equal to 0, our u will be equal to our d naught, and when x is equal to a, we get our u will be equal to d naught plus alpha times a. So we get our capacitance C will be equal to epsilon naught A, this comes as our d naught, and we have this is d naught plus alpha times A, and here we are left with our 1 by u, and this is dx upon alpha, and alpha we can take outside, we get this epsilon naught A upon alpha, and we get this as 1 upon u will be natural log of u, and it comes as d naught plus alpha A. Now we can just substitute the limits, we get epsilon naught A upon alpha, natural log of this will be upper limit minus lower limit, which we can just substitute in the denominator, and we can write this as epsilon naught A upon alpha, this comes as natural log of 1 plus alpha A divided by d naught, and this we can compare with one of the formulae, that is natural log of 1 plus x is approximately equal to x minus x square by 2, or expansion. So we just substitute it here, and we get this as capacitance C will be equal to we have this as epsilon naught A square divided by d, and 1 minus, and here we have our alpha A divided by 2. So this is our final capacitance, and we get this as alpha epsilon naught A square 1 minus 2d, I missed here d. So it comes as epsilon naught alpha A 1 minus 2d. Option 4 is correct. Option 4 is correct. Next question. We are given a parallel plate capacitor has a plates of area A separated by a distance d between them. It is filled with a dielectric which has a dielectric constant that varies as k of x is equal to k times 1 plus alpha x, where x is the distance measured from one of the plates. If alpha multiplied by d is very much smaller than 1, the total capacitance of the system is best given by the expression. So here we are given that we have a parallel plate capacitor, and it says that dielectric varies. Suppose we take this point as x equal to 0, and separation between this final point will be our x equal to d, because the separation between the plates is given as d, and the dielectric constant varies with respect to x, and that is governed by the equation that k of x is equal to k 1 plus alpha times x. Okay, it means it is going to vary towards the right side in this direction. Area of the plates is A, and we are going to consider a small strip of thickness dx, and it is at a distance of x from the origin, that is one of the plates. So this is going to behave as a parallel plate capacitor. So we consider a thin slab of thickness dx at a distance x from one off plate. And in this particular case, we have considered left plate. And area of the plate is A and thickness is dx. So we can say for area is our A, thickness is our dx, and dielectric constant, that is our k of x, is equal to k 1 plus alpha times x. So we can write the capacitance d of c, which is our epsilon multiplied by area, and dielectric constant, that is our k of x, that is our k 1 plus alpha times x, and the thickness distance between plates, that is our d of x. Here we have to please try to understand this d of x is independently acting as a capacitor. Okay. This is a small capacitor. This is thickness is distance between the plates is dx, area is A, and its dielectric constant is varying from left to right and governed by the same equation. And we can draw a multiple number of you can say strips, like not strip but slab between the plates. Okay, and first one here, then we can now draw also somewhere here. So therefore the total capacitance C will be equal to integration 0 to d, and this is dc. We substitute value of dc, we get c is equal to 0 to d, and we have this epsilon a k times 1 plus alpha x divided by dx. Okay, but in this case, please remember that all these capacitors will be connected in series. Okay, so therefore I have to correct my formula that my total capacitance, if given as C, it can be written as 1 upon C is equal to integration 0 to d, and this get us as 1 upon dc. So we can write this as 1 upon C is equal to 0 to d, and we get this as dx upon epsilon a k times 1 plus alpha x, and we can take it as common, epsilon k integration 0 to d dx, and this comes as 1 plus alpha x. Now we are only interested in the integration part. So we can integrate separately 0 to d dx and 1 plus alpha x. This will be giving us natural log of 1 plus alpha d and multiply by 1 by alpha. So this gives us 1 upon C is equal to 1 upon epsilon a times k, and this comes as 1 upon alpha natural log of 1 plus alpha d. So from here we get our C capacitance will be equal to, this is our epsilon a k alpha, and this is our natural log of 1 plus alpha d, and we are given that this alpha d is very much small than 1. Therefore we can approximate that our natural log of 1 plus alpha d will be approximately equal to alpha d minus alpha d whole square divided by 2 plus and so on. So this can be approximately equal to alpha times d. So we get our C will be equal to epsilon a k alpha, and this comes alpha times d. Here alpha and alpha cancels out, so we get this will be equal to our epsilon a k times d. Okay. So here this calculation is that I have ignored this higher order part. Okay, but we can include that part also. It's not a big issue, because as per the result, so we are going to consider these two parts. So we can write that our natural log of 1 plus alpha d is approximately equal to alpha d minus alpha d whole square divided by 2. And we are going to use this entire higher order, and we can write this will be equal to C is equal to epsilon naught K, and this was A times alpha, and here we have our alpha d minus this will be alpha square d square upon 2, and we can take alpha d as common. So from here we get this as epsilon K A alpha, alpha d is common, this comes as 1 minus alpha d divided by 2, and alpha cancels out, and we get that our C will be equal to epsilon K A upon d, and this can be written as 1 minus alpha d to raised power minus 1. And for this part we can use our binomial approximation rather, which gives us that alpha K A divided by d, giving us 1 plus alpha d divided by 2. So this is our final answer. So you can say we are going to solve this as by using binomial approximation, or we also can call it a binomial expansion, and then we can approximate it. So we get this as AK, and we have this option number 1 is correct. One is correct. Next question. We are given a 60 picofarad is fully charged by a 20 volt supply. It is then disconnected from the supply and is connected to another uncharged 60 picofarad capacitor in parallel. The electrostatic energy that is lost in this process by the time the charge is redistributed between them is in nanojoule. Okay, so we have to find out the energy lost. So we are given that initially we are having one capacitor. Let us suppose that we have a C1 and it is connected to a voltage supply. Let us suppose that is a V, which is given as 20 volt. And initially the charge, let us suppose, is Q1 here, and after that it is connected to another capacitor whose value is same but that is uncharged, and both are connected in parallel. So we have this as our C1 and it is connected to another capacitor. Let us suppose that is our C2, and okay, so we have to find out the charge loss, we have to find out the energy lost in this entire process. So we can divide this into two parts, and keeping in mind that our total charge will be constant, conserved rather, okay, and initial charge on C2 was equal to 0. So we can say that Q2 was equal to 0 initially, okay, because it was uncharged, and therefore we can find out the initial energy stored in C1. Initial energy stored. So initially only C1 was charged, or rather we can say connected to supply. So entire initial energy, let us suppose that is given as our EI, will be our half C1 V square. We can write this our E1 is equal to half into 60 into 10 raised to power minus 12, and V square comes as 20 multiplied by 20, and this will be coming as 12 nano joules. And after final energy, when C1 and C2 connected in parallel, so we can say final energy, which basically means C1 and C2 are in parallel. So we can find out the total capacitance. Equivalent capacitance, let us we call this as C, or C prime rather. C prime will be equal to C1 plus C2, both are same, so we can write there 2C, 2C1 rather, and value is 60, so this comes as 20 picofarad. So we have equivalent capacitance C prime, and the total charge is going to be conserved. So we can say that total charge remains conserved, but the voltage becomes half. Because the charge will be equally distributed between the two capacitors because they are identical. So you can, because charge equally distributes between identical capacitors. Identical capacitors. Therefore, it is also going to have our V by 2, and here also we are going to have V by 2. So we can write our equivalent, our final energy let us call this as our E final, will be equal to half, we have this as C equivalent, that is C prime, and our V2 whole square. C prime is our 120 and V is our, or let me write it other way, so we get this as our half multiplied by 2C and multiply by V square by 4. So we get our final energy is equal to half CV square, okay, because this goes by 2, and one second, okay, so this can be written as half of half CV square, and half of CV square is nothing but our initial energy. So we can say this will be half of our initial energy, and initial energy was our 12 nanojoule. So we can write this as half into 12, giving us 6 nanojoules. So this comes as 6 nanojoules. Next question. It states that, one second. By default, we have to find out the lost energy, not the final energy. So we can say energy lost will be equal to initial energy minus final energy, which gives us 12 minus 6, giving us 6 nanojoules. So by default, the answer is 6, but this last step I missed it. Next question. We are given the parallel combination of two air-filled parallel plate capacitors of capacitance C and N times C is connected to the battery voltage V. When the capacitors are fully charged, the battery is removed, and after that a dielectric material of dielectric constant K is placed between the plates of first capacitor. The new potential difference of the combined system is. So here we are given, we have two capacitors. Let us suppose this is C1, which is equal to C, and it is connected in parallel with other capacitor. Let us suppose that is our C2, which is N times C, and they are both connected with in parallel with the voltage source, that is our V. Now in the second part, the battery is removed and a dielectric material is placed between the first capacitor, that is our C1. So in between C1, a dielectric material is placed. Let us suppose its capacitance becomes now C1 prime, and our C2 is as it is. So this is our C2, which comes N times C. So we have to find out the and dielectric constant is K. So obviously we can say that our C1 prime is equal to K times C. K times C1 and then K times C. And in the first case, we can say that this is our initial and this is our final. Therefore, for initial condition, let us assume that the charge on C1 is Q1, charge on C1 is our Q1, which will be equal to C1 times V, which comes as CV. And similarly, charge on C2 let us suppose that is our Q2, it will be coming as C2 times V, and this comes as NCV. And in the second final condition, there is no external voltage source, so the charge will be conserved. So we can find out there for initial condition the total charge. Therefore, you can say total charge on the system, let us call this as Qt, will be equal to Q1 plus Q2. We substitute value of Q1 and Q2, we get our total charge Qt is equal to CV plus N times CV. CV we can take common, this comes as 1 plus N. So this is our total charge. And final condition, is battery is removed and dielectric is inserted. Dielectric is inserted in only first capacitor. So from here we can say the capacitance of first capacitor which we called C1 prime will be equal to K times C1, or we can say K times C. And for second capacitance, that is as it is. So we can say for second capacitance our C2 is our N times C. Now we can find out the total capacitance. Total capacitance, let us call this as CT, which will be a series combination, parallel combination of C1 prime and C2, which gives us KC plus NC. Therefore we get our CT, with C we can take common, this comes as K plus N. And let us suppose that the common voltage across both is V prime, because both are in parallel, so they are going to have same potential voltage. So we say that new common voltage, let us suppose a V prime, and our charge will be conserved. Charge is conserved, therefore our which will be equal to QT, and QT can be written as our CT multiplied by V prime, and Q total we already know is our CV 1 plus N. This comes as 1 plus N multiplied by C, and V is equal to total CT we found out is our C times K plus N multiplied by V prime, and it is, so we get our V prime, and we can cancel out our C and C. We get our V prime is equal to 1 plus N divided by K plus N and times V. So this is the final potential difference across the capacitor, and we get this as option 3 is correct. Option 3 is correct. Next question. We are given 10 charges are placed on the circumference of a circle of radius r with a constant angular separation between successive charges. Alternate charges 1, 3, 5, 7, 8, 9, 1, 3, 5, 7, 9 have charge plus q, while 2, 4, 6, 8, 10 have minus q each. The potential V and electric field E at the center of circle respectively will be. So in this case, we have to remember that the electric field due to a positive charge at a distance r will be away from the charge, and for our negative charge that will be towards the charge. So we have to keep this in mind. So we are given that, and that is r is a distance. So in both the cases, positive and negative, if they are charges up at same distance, electric field will be same, but direction will be opposite. So we are given that we are having plus q charge, and that is placed at 1, 3, 5, 7 and 9, and we have minus q charge, and that is placed at 2, 4, 6, 8 and 10. And we know that we are supposed to find out the electric field as well as the potential. So we can just draw an approximate figure for that. And let us draw a circle, and we have total, suppose this is center, and we are having a total of 10 charges. And on the other side, more or less, it is not symmetric, but more or less we get the idea. And suppose we start from here 1, this is about 2, 3, 4, 5, 6, 7, 8, 9 and 10. And we are given 1, 3, 5, 7, alternate we have a plus charges. So this will be plus q, plus q, plus q, plus q and plus q. And then we are having minus q, minus q, minus q, minus q, minus q and minus q. We have to find out at the center. Let us suppose that center is O, and the radius of this circle is suppose r. So each charge is at the same distance with respect to center O. Okay. And obviously the magnitude of electric field is going to remain same because the charges are same and our distance is also same. So let us write that magnitude of electric field due to each charge at the center is, let us suppose, given as E. So like I said, the positive is going to have electric field away and negative is going to head towards itself. So let us draw. So because of this charge placed at 1, we are going to have electric field that will be in this direction, and that is because of this one charge, and because of this minus q charge we are also going to have electric field that will be towards itself. So therefore the net electric field will be over 2 times E. Similarly, for every charge we are going to have an electric field that will be towards our the negative charge. The magnitude will be same. So this will be also coming as 2E, and this will be also over 2E, and what else, this is remaining. So this will be also over 2E. So therefore only in terms of electric field we can just draw it. So this will be over 2 times E. This will be also 2 times E, and total will be 1, 2, 3, 1 is missing. Yeah, 1 second. This one. This will be also 2E. So we get this E also over 2E, and we are left with only 2, and that will be, one will be in this direction, that is about 2E, another one will be in this direction, that is also over 2E. And if we so therefore from here we can say that even if we try to find out their resultant, from the figure itself it is coming clear that all these electric fields will be placed at same angle. The angle between them will be same. And we can say that the charges are placed symmetrically charges are placed symmetrically. Therefore the resultant electric field at the center will be equal to 0. So it means our electric field at the center is 0. And now let us find out the potential at the center. And potential at a distance r, let us suppose given as V, will be equal to K times Q upon R. And because potential is scalar, so we can just directly add respectively for all the charges. Therefore we can say for all charges our total potential at the center will be equal to K divided by R summation I to 10, and this is our Q of I, and we are only interested in their summation, and we can just write it as summation I is equal to 1 to 10 Q of I. We open the summation, we get this as Q1 plus Q2 plus Q3 4 5 6 7 8 9 and 10, and we know that alternately they are negative, alternately the charges are opposite and magnitude is same. So we can write this will be equal to our plus Q minus Q plus Q minus Q plus Q minus Q plus Q minus Q plus Q minus Q. This comes as, so these are the 10 charges. Obviously they are going to cancel out each other. Net charge will be equal to 0. Therefore our potential at the center will be equal to 0, which is suppose given as V. So both electric field and potential at the center is 0, so option 1 is correct. Next question. We are given two isolated conducting sphere S1 and S2 of radius 3 by 2 times r and 1 by 3 times r have 12 microcoulomb and minus 3 microcoulomb charges respectively and are at a large distance from each other. They are now connected by a conducting wire. A long time after this is done, the charges on S1 and S2 are respectively. So we have two spheres. Suppose this is our S1 and this is S2. Radius is its radius is given as suppose 3 by 2 times r, and here it is given by 3 times r. And the charge on the first one, let us suppose that Q1 is 12 microcoulomb. The second one is our Q2 is minus 3 microcoulomb. Then they are connected through a wire. So we have a S1 and S2 and they are connected through a wire. So this comes as 3 by 2, radius will be obviously same, 1 by 3 times r, and the charge transfer is going to take place and resulting in the same potential. Okay, so suppose this is having a V1 potential and this is our V2 potential, then when they are connected, V1 should be equal to our V2. And finally, let us assume the charge on first one is Q1 prime and the second one is our Q2 prime, which we are supposed to find out. And we are going to solve this potential part, and we know that the potential on a conducting sphere of radius r and charge q, say potential on a conducting sphere of radius capital R and charge capital Q, this is given as V is equal to K times Q upon R, and we can write this as our both the spheres. So we can say for sphere S1, V1 is equal to K, and charge we assumed is our Q1 prime upon radius is 3 by 2 times R, and for our S2 we can write this as V2 is equal to K Q2 prime divided by 1 by 3 times R. When they are connected, the potential has to be same. So we can say V1 is equal to V2. So we substitute it, we get this is K Q1 prime, and this comes as 3 by 2 times R is equal to K Q2 prime divided by 1 by 3 times R. And here R and R goes away, K and K also goes, and we get this as this is 2 by 3, 1 by 3. I think it should be 2 by 3, otherwise it is not going to solve. So this comes as 2 by 3 and this comes as 2 by 3, and here also it will be 2 by 3, and this also comes as 2 by 3, and this 3 and 3 goes away. So we get that our Q2 prime is equal to Q1 prime is equal to 2 times Q2 prime. So this is the total charge after they are connected, but charge should be conserved. Okay. So we can say the total charge is conserved which basically means that initial charge should be equal to final charge, and initial charge is our Q1 plus Q2, and it is given as 12 minus 3, which comes as 9 microcoulomb, and the final charge is our Q1 prime plus Q2 prime. So we already know relationship between Q1 prime and Q2 prime, therefore we can write that Q1 prime is equal to twice Q2 prime. Therefore, we can write this will be equal to our twice Q2 prime plus Q2 prime is equal to 9. And we get this as 3. So we get this as Q2 prime will be equal to 3 microcoulomb, which gives us that our Q1 prime will be equal to 6 microcoulomb. So the option is S1 is having our Q1, that is our Q1 is 6, yeah, 3 is correct. Option 3 is correct. Next question. We are given a concentric metallic hollow sphere of radii r and 4r hold charges q1 and q2 respectively. Given that surface charge densities of the concentric spheres are equal, the potential difference V of r minus V of 4r is. So here we are given that we have two concentric So we have a concentric inner radius is given as r and outer radius is 4 times r. And for inner part, we assume that the charge is our q1 and the outer we assume the charge is our q2. And we are given that their surface charge densities are equal. And if their surface charge densities are equal, we can say we are given surface charge density are equal. So we start from there. Our surface charge density, which is our sigma, is equal to q upon 4 pi r square. So we have two surfaces. So for one, let us assume it is sigma 1 and other it is our sigma 2. Therefore, we can write that our sigma 1 is equal to q1 upon 4 pi r square and we have sigma 2 is equal to our q2 upon 4 pi, radius is our 4r whole square, and we are given that the radius are their densities are equal. So we can write that sigma 1 is equal to sigma 2. Therefore q1 upon 4 pi r square is equal to q2 upon 4 pi 4r whole square. And here we can cancel out 4 pi and 4 pi, and r square will be also going away, so this will be coming as 16r square. So our r square and r square goes away, and we are left with that our q1 is equal to q2 upon 16. Now we are supposed to find out the potential difference. So we know the relationship between their charges, and we can write that potential due to charged shell. And for our charged shell, we know that the potential at a point outside or on the shell is same as a point charge at the center. Therefore we can write that our potential at radius r, and we can say if r is equal to capital R on inner shell, therefore we can write this as V of R will be equal to 1 upon 4 pi epsilon naught. Let me write it in the lower part. So we can write this as V of R will be equal to K times Q1 upon R plus Q2 upon 4R. And for the second one, we can write potential at radius 4r, and here we can say at small r is equal to 4r, that is our on outer shell. We can say V of 4r will be equal to K Q1 upon 4R plus Q2 upon 4R. We need to find out their difference. So we can write that our V of R minus V of 4R. We substitute the value and we can take R K as common. So this will be coming as K, and we can take this as our first part is our Q1 upon R plus Q2 upon 4R minus Q1 upon 4R and plus Q2 upon 4R. Now we can just solve it, and we get from here will be equal to K, and obviously this Q2 and Q2 will cancel out each other, and we will left with only Q1 upon R minus Q1 upon 4R. This gives us K, and we are going to have 4R will be LCM, and or rather we can say, yeah, it's not a big issue. This comes as 4 minus 1, that is about 3 times Q1, and we already know relationship between Q1 and Q2, so we substitute it here. We get this as our K times 3 by 4R, and Q1 we found out Q2 by 16. So this comes as our Q2 by 16, which gives us K times 3Q2, and this comes as 64 times R. So we get this as there is some mistake on my part. One second. Answer is in Q1 form. Okay, answer is in both Q1 and Q2. So for Q2, it is thrice Q2 and Q2. Okay, let me check. So I can write that my VR minus V of 4R is equal to K times 3Q2 64 times R. And in terms of Q1, okay, and this is VR minus V of 4R is equal to K, and this comes as 3Q1 upon 4R. So let me check which of the option is correct. So this comes as 3 by, there is some mistake somewhere, 1 4 is missing. At least it is not in terms of Q2, that's for sure, but in terms of Q1, either it will be 16 or it will be 4. So it is okay. So this comes as 3 upon Q1, and K is 1 upon 4 pi epsilon naught. So this comes as 16 pi epsilon naught times R. Okay. I think this should be the correct one if I'm not wrong. So it comes as 3 by 16. Yeah, it's correct. Thought I did some mistake. So option number 2 is the correct one. Option 2 is correct. Next question. We are given a charge Q is distributed over two concentric conducting thin spherical shells, radius r and capital R. Capital R is greater than small r. If the surface densities of the two shells are equal, the electric potential at the common center is. Basic figure is given to us, and we have two, that is inner as well as outer, and let us assume that the inner shell is having a charge of Q1, outer is having a charge of Q2. Surface density of inner is sigma 1 and for the outer is sigma 2. And say that let the charge on inner shell is Q1 and outer shell is Q2, and we also given that a total charge is Q. Therefore, we can say that the Q will be equal to Q1 plus Q2. We are given that the surface charge densities are equal. So we know the formula for surface charge density. Sorry, once again. So we know the formula of surface charge density, that is, we can say our surface charge density that is our sigma is equal to our charge oblique 4 pi r square. So for we have two shells, inner and outer, so we can write our sigma 1 will be equal to our Q1 upon 4 pi r square. Inner is having a smaller radius, that is small r square, and for outer it will be coming as sigma 2 will be Q2 upon 4 pi r square. But sigma 1 and sigma 2 are equal. Therefore, we can write that Q1 upon 4 pi r square is equal to Q2 upon 4 pi capital R square. 4 pi cancel out. So from here we get our Q2 is equal to Q1 times capital R square divided by small r square. So this gives a relationship between the two charges. And we are also given that the total charge is Q. So we can write that total charge which is a Q is equal to Q1 plus Q2. We substitute value of Q2, we get this as a Q1 plus Q1 times R square upon small r square. Therefore, we can write our Q is equal to Q1 we take as common, we can write this as 1 plus r square upon small r square. So from here Q1 is equal to capital Q 1 plus r square upon small r square. So this gives us that our Q1 is equal to r square upon capital R square small r square multiplied by total charge Q. And from here we can also find out our Q2, which will be equal to our Q minus Q1. So this gives us that our Q2 will be equal to this comes as our capital R square divided by R square plus R square times Q. So we found out the charges on the respective shells, inner as well as outer. we know the potential. So we can say potential at the center, potential at the center, and we have two shells. So one by one we are going to take them and solve them. First of all, we say potential, because they have common center, potential at the center due to charge. First charge is our Q1 and radius is small r. Let us suppose that is our given as V1. So V1 will be equal to 1 upon 4 pi epsilon naught Q1 upon R. And for the outer, we are having this charge as Q2 and the radius is capital R. Let us suppose that is our V2 will be coming as 1 upon 4 pi epsilon naught Q2 upon capital R. So total potential will be V1 plus V2. Total potential, let us suppose that is our V will be equal to V1 plus V2. We substitute V1 plus V2, we get our V is equal to, we can take 1 upon 4 pi epsilon naught as common. This will be our Q1 upon R plus Q2 upon capital R. We already know the relationship between Q1 and Q2, which we substitute in place of Q2. So we get this as 1 upon 4 pi epsilon naught Q1 R plus, this comes as our Q1 R square divided by R times small r square. Q1 is, Q2 is, and now we are left to solve it. We can take Q1 as common. This is Q1 upon 4 pi epsilon naught, and we are left with this 1 upon R plus square cancel with this R, and we get this as R upon R square. And we get from here that the potential will be equal to Q1 upon 4 pi epsilon naught, our R square will be our LCM, and we get this as R plus capital R. And the options are in terms of total charge. So we substitute Q with respect to total charge. So this gives us 1 upon 4 pi epsilon naught, and we have this is R plus capital R divided by R square, and Q1 in terms of total charge Q is our Q R square divided by R square plus capital R square. Here R square and R square goes away, so we get our V is equal to Q upon 4 pi epsilon naught, and we get this as R plus capital R divided by R square plus capital R square. So this is our required potential, and the option number A is the correct one. 1 is correct. One is correct. Next question. We are given that a solid sphere of radius r carries a charge q plus small q distributed uniformly over its volume. A very small point like piece of it of mass m gets detached from the bottom of the sphere and falls down vertically under gravity. This piece carries a charge q. If it acquires a speed v when it has fallen through a vertical height y, see figure, then assume the remaining portion to be spherical. Okay, we have to find out the final velocity at this particular point. So initially we are having a solid sphere of radius r, and the total charge on this sphere is given as q plus small q, and a mass m drops from the whole sphere, and the charge carried out by this mass m is small q. Okay, so from here we can say that this sphere carries a charge q and small m is carrying a charge small q. So if small m is attached with the sphere, solid sphere rather, then it is going to have a total charge of q plus small q. And we are going to find out the velocity at a distance y from this solid sphere. So first of all, let's find out what will be the electric field inside a solid charge sphere. So electric field inside a uniform charged solid sphere. Solid sphere at a distance small r, which is less than equal to capital R. So we can write the electric field at a distance r will be equal to k times, and we have this is charge enclosed within the distance of r divided by small r square. And this charge enclosed at a distance of r will be equal to total charge multiplied by our small r cube divided by capital R cube. So we can write that electric field at a distance r will be equal to k times, we have this as charge total and r cube divided by our capital R cube, and finally divided by r square. This gives us k, and we have this as q total multiplied by r and divided by r cube, because this square goes by this cube. And so this particular equation, or part of the equation, we can assume to a certain constant value. Let us suppose that we can assume k once again, it doesn't matter, and we can say that our E of R is equal to, let us call this as K1 times R, and where this K1 is equal to our K times Q total divided by R cube. So from the expression we can say our electric field varies linearly with the distance. And initially the mass M is at a distance R, and finally it will be at a distance of R plus Y. From the center. So we can say that direction of electric force on the piece which is dropped. Direction of electric force on the piece, and initially the piece is at the bottom of the sphere. So you can see the piece is at the bottom of the sphere initially, or we can say our small r is equal to capital R, and after detaching it moves down by distance y. Therefore our R becomes capital R plus Y. So it means our sphere this piece moves from the distance R to R plus capital Y. Now we can find out the work done by the forces rather. Work done by the forces. First will be our gravity. So we can say work done by gravity. Let us call this as Wg will be equal to our mgy. And next is our work done by the electric force. Work done by electric force. So first of all, let's find out our force, and let us call this as We, and our force. Okay, so let's find out the electric force. Electric force on the piece. Let us call this Fe, which will be equal to Q times the electric field, and we get here Fe will be equal to Q times K1R, and we substitute value of K1, we get this as Q times 1 upon 4 pi epsilon naught, and this is Q total times R divided by R cube. And we can find out, or we can say we can use the work energy theorem. Work energy theorem, and this net work done will be converted into the kinetic energy. Okay, so we can say that net work done on the piece is converted into kinetic energy, or we can say that work done net will be equal to change in kinetic energy. Change in kinetic energy, initially it was at rest, so change in kinetic energy will be equal to over half mv square, and this W net is equal to our work done to gravity and work done because of the electrostatic force. And so this is equal to half mv square, and we are supposed to find out this work done due to electric field. We already found out the force, and so therefore we can say that our We will be equal to force and small distance dr, and the piece moves from R to R plus capital Y, R plus Y, and we can write this as our R plus Y, and Fe is our Q K1 times R times dr. We can take common, so this comes as this comes as our Q times K1, and we have this is R plus Y, R and dr. So we get our work done due to electric field is K1 times Q, and this will be coming as R square by 2, so this comes as 2, and we will be left with our R plus Y whole square minus R square. And if we open it and solve it, we get work done will be equal to K1 Q upon 2 R square, and R square is going to cancel out, so we get this as 2RY plus Y square. Now we can easily substitute in this equation. Let us call this equation as 1. So from equation 1, we get that our half mv square is equal to mgy minus, we have this as k1 upon 2 ry plus y square. And now it's only calculation left, so we get this as v square is equal to, we multiply, this comes as 2mgy upon m minus q k1 into 2 divided by m divided by 2, and this comes as okay, this is 2 here and 2 here and 2 here. This is correct, yes, and we can take 2 as common from here also, so we get this as y square upon 2 plus ry, and this is also over 2. One second, this r square by 2, this is correct, 2ry and 2ry, okay. So here 2 goes with 2, and we get this will be equal to our v square, and here m goes with m, so we are left with this is 2gy minus one second, this is q total, yeah, my mistake, this is q total, and this is also our q total. Let me correct it, q total, and here also q total, so this comes as qt, and this also our qt, and here also will be our total charge. So this case is our two gy minus there is some problem, need both, yeah, because this q is because of this I missed it, so this comes as q q q q, so this comes as q multiplied by q total into k1, and this is multiplied by 2, and we have this as ry plus y square by 2 and divided by m. Okay, so from here we can take y as common, this will be y as common because the answer is in terms of taking 2y as common. Okay, so let me take 2y as common, so this comes as about 2y, and we are left with our g, and this will be a minus, we have this as q times q total, and we have this as k1 divided by our m, and we are having this will be our, one second, and G, this comes as R plus y by 2. I think this should be, this gives us V square root. Okay, we have our G and we have our, so option number 4 is correct. Four is correct. Next question. We are given a 2-point charges. One second. Yes. Oh, sorry. I didn't sort it out completely. And we need to specifically solve this part. And for that, let me write that 1 upon r plus y minus 1 upon r. This will be giving us there is some problem. R cube. Okay. So we get this as 2 of y g minus q, and here q total is our capital Q divided by m, and the value of K1 is our K upon r cube, which gives us 1 upon 4 pi epsilon naught r cube, and this comes as r plus y upon 2. And so we are going to solve this part. So we get this as 1 upon r cube, r plus y by 2, and this gives us 1 upon r square plus y upon, or let me take This can be written as r square, r into r square, and this will be our r square. So this gives us 1 upon r plus y upon 2r. And we can write this will be equal to our 2r, giving us okay. So we can just reformulate it, and we can write this as 1 upon r plus y minus 1 upon r. This will be giving us, and this I missed something. First of all, let's put two y g plus q upon q divided by m, and this comes as 1 upon 4 pi epsilon naught r cube and we have here r plus y by 2. This is our minus, and this gives us 2y g plus q multiplied by q, and here we have 4 pi epsilon naught r and r plus y. So this gives us our v square. So now it's correct one. So we have our option 4 is correct. Next question. We are given that 2-point charges 4q and minus 4q are fixed on the x-axis at x equal to minus d by 2 and at x equal to d by 2 respectively. If a third point charge q is taken from the origin to x equal to d along a semicircle as shown in the figure, the energy of the charge will be. So basic figure is given to us. So we have a initial point charge which was initially at origin, then it is taken at a distance d. So this entire distance is our d, and this minus q is at d by 2. So position of this point charge with respect to minus q, distance position with respect to minus q will be same, that is our d by 2. So we have to find out the energy. Okay. So we can say change energy, which will be potential difference between the 2 points and multiply by the charge, that is q. So let us call this as point as A and this point as B. So we can say that electrostatic potential energy change electrostatic potential energy change, that is our delta of U, will be equal to Q, and we have this as VA minus VB. Here VA is our initial point and B is our final point. Now if we see closely, with respect to minus Q, the distance between initial point, that is point A, and the final point is same. Okay. So which basically means that only this 4Q is going to contribute towards the potential. Okay. So we can say that initial position of point charge with respect to minus q is d by 2, and final position of point charge with respect to minus q is still d by 2. One time it's on the left side and other time it's on the right side. Therefore, we can say that the potential due to minus q initially will be equal to potential due to minus q finally. So which means that no net effect on delta U. No net effect on delta U. So we are going to calculate the potential difference, or we can say potential change in potential rather, only because of 4Q. So let's find it. Potential due to plus 4Q. Potential due to plus 4Q at initial position at initial point, and initial point is our A. So we can write this as our V initial, or let us call this as VA, will be equal to 1 upon 4 pi epsilon naught 4Q divided by D by 2. And this gives us our VA will be equal to, we get this as 1 upon 4 pi epsilon naught 8Q divided by D. Now we come to the final point. Final point, which is our B. So we can say our VB will be equal to 1 upon 4 pi epsilon naught multiplied by 4Q divided by 3D by 2. This gives us VB will be equal to, this will be over 1 by 3 times 1 upon 4 pi epsilon naught, and this will be 8Q. Now we can find out the change. Change, that is delta of U, will be equal to Q times VA minus VB. We substitute the values, we get this as Q, and we are going to have, this is 1 minus 1 by 3, sorry, 1 minus 1 by 3, and 8Q upon 4 pi epsilon times D will be common. So this comes as 2 by 3. 2 by 3 will be our 16. This will be our 16 by 12, and Q square pi epsilon times D. And we can just cancel it. This goes by 4 and this goes by 3. Therefore our change delta of U will be equal to 4 by 3 and Q square upon pi epsilon times D. This is our change in energy, decrease in energy rather, and this comes as 3Q square, option number 4, sorry, decrease. Yeah, decrease in option number 2 is correct. Next question. States that hydrogen ion and singly ionized helium atom are accelerated from rest through the same potential difference. The ratio of final speeds of hydrogen and helium ions is close to. So here we are going to find out, or we can say we are going to use conservation of energy. So kinetic energy gained is equal to electrical potential energy. So we can say energy conservation and this energy conservation gives us that kinetic energy gained will be equal to electrical potential energy. electrical potential energy, which we can write half mv square is equal to q multiplied by our potential. So we can say our V is equal to 2qv divided by mass m and its square root. So this is the general formula for the velocity. Now we can divide this velocity equation as per the particle. So first is our hydrogen ion. So we can say for hydrogen ion, our charge will be equal to our electron and mass will be our mass of proton. So therefore we can write our V1 will be equal to 2eV divided by mass of proton and its square root. And next is singly ionized helium. So we can say for He positive, our Q2 is our E and our M2 is equal to 4 times mass of the proton. So we can write our V2 will be equal to twice EV divided by 4 times mass of proton and its square root. 1 by 2 we can take as common. So this comes as twice EV divided by mass of proton, which is nothing but our V1. So this comes as half of V1. So we need to find out ratio of V1 by V2. So we can say V1 ratio V2 will be equal to 2:1. So option 1 is correct. Next question. We are given two capacitors of capacitances C and 2C are charged to a potential difference of V and 2V respectively. These are then connected in parallel in such a manner that positive terminal of one is connected to the negative terminal of the other. The final energy of this configuration is. So we are having two capacitors and so let us suppose this is our first capacitor. Capacitance is C1, which is given as C, and the voltage potential difference it's charged is our V. And then we have our second one, that is our C2, which is given as 2C, and the voltage it is charged to given as a 2V. And then they are connected in parallel. Suppose this is positive and this is negative, such that it will be negative and positive. So this will be our C1 and this is C2. So in the first case, let us suppose charge is Q1. So Q1 will be equal to C multiplied by V, and here it is charge is Q2, which will be coming as 4 times CV. Okay. And we have to remember that they are connected in parallel such that opposite charge plates are connected with each other. Okay, so there will be some redistribution of the charge, or we can say cancellation of the charge. So let's find out the net charge after connection. Net charge after connection. and after connection the charge on C2 will be of the opposite polarity. So we can say this is our minus of 4 times CV because it is connected with opposite polarity, and for C1 it will be as it is, that is our C. So we can say our net charge after connection, let us call this as QT, will be equal to our CV plus minus of 4 times CV. This gives our total charge QT is equal to minus 3 times CV. And they are connected in parallel, so equivalent capacitance that is our C equivalent will be equal to C1 plus C2, which comes as C plus 2C is equal to 3C. So we can easily find out the final voltage. Final voltage V final will be equal to total charge divided by C equivalent. Total charge is our minus 3 CV and C equivalent is our 3C. 3C goes away. This comes as our minus V. We are supposed to find out final energy. So the only this is minus V means polarity, magnitude. We are interested in magnitude, that is our V. So we can say our final energy that is our U is equal to our half C equivalent and V final square, which comes as half C equivalent is our 3 times C, V final is our minus V whole square, which comes as 3 by 2 CV square. So option number 1 is correct. Next question. In the circuit shown, the charge on 5 microfarad capacitor is. So here we have two voltage sources, 6 volt as 6 volt, and we have 3 capacitors. Let us suppose C1, C2 and C3. And accordingly, let us suppose the charge is our Q1, Q2 and Q3. And (6 volt). So obviously let us call this as point A, B, C, D and E. So potential at E will be 6, at A will be also 6, similarly at D will be 6 and at C will be also equal to 6, and at B let us assume that is our V. And in steady state condition all the capacitors will be acting as open circuit. Okay. So here we can just find out that what will be our charge Q1, or we can say for junctional analysis at B we can use just our Q1 plus Q2 plus Q3 is equal to 0. You can say that this is giving us Q1 plus Q2 plus Q3 is equal to 0. And Q1 is charged on C1, so we can say our Q1 will be equal to potential difference multiplied by C1, and potential difference will be our VA minus VB, and VB will be on the higher side, so we can say this will be our VB minus VA minus VA divided by its capacitance, which gives us VB is equal to V minus 6, and this is about 2 microcoulomb. Similarly, we can write our Q2. Q2 will be equal to V minus 0, so this comes as V minus 0 because it is common potential 0 multiplied by 5, this giving us 5 microcoulomb. And Q3 will be equal to, we are having this as 6, so this will be VB minus VC and multiply by 4. This gives us our V minus 6, 4 microcoulomb. Now we simply substitute them and add. So we get this as V minus 6 multiplied by 2 plus 5 plus V minus 6 multiplied by 4 is equal to 0. So this gives us 2V minus 12 plus 5 plus 4V minus 24 is equal to 0. And this will be our 36. Sorry, this is V. So we get this as 36, and we have here 11V. So 11V is equal to 36, which gives us V will be equal to 36 by 11 microvolts. And we need to find out the charge on 5 microfarad. So we can say Q5, or we call this as Q3, is equal to, Q3 is our V minus, so this comes as, one second, Q3 is our V minus 6 multiplied by 4. So this comes as 36 upon 11 minus 6 multiplied by 4 microcoulomb. And one second. Sorry. Here I have written, this is Q3 and Q2. Q3, and this is Q2. My mistake. So we get our Q3 will be equal to 36 upon 11 multiplied by 5 microcoulomb, which gives us 180 by 11 and approximately equal to 16.36 microcoulomb. Option 1 is correct. Next question. It states that A capacitor C is fully charged with voltage V0. After disconnecting the voltage source, it is connected to in parallel with another uncharged capacitor of capacitance C by 2. The energy loss in the process after the charge is distributed between the two capacitors is. So here we are having that there are two capacitors. Suppose that is C1, which is given as C and is connected in parallel with voltage V0. In the second part, we are connecting this our C1 in parallel with another capacitor C2, suppose, and C2 is our C by 2 and C1 is C. We have to find out the loss in energy, and C2 is initially uncharged. So initial energy stored that will be only because of this C1. So we can write this as our EI is equal to our half C1 V0 square. And after, let us call this as final condition and this as initial condition. So we can say for final condition, we are given that C1 and C2 are in parallel. C1 and C2 are in parallel, therefore equivalent capacitance let us call this as C equivalent will be equal to C1 plus C2, and total initial charge will be conserved, okay. And C is our, we can just write it later on value, and we can say our total initial charge let us assume that is our Q1. So we can say our Q1 will be equal to our C1 times V0, and the initial and final charge will be same. So total initial charge is Q1, and let me rephrase it. Total initial charge is our Qi, which will be equal to Q1 is equal to C1 times V0. And from charge conservation, we have final charge is equal to initial charge. Therefore, Q final is equal to Q initial, which gives us that Q final will be equal to C1 times V0. And both the charges are connected, both the capacitors are connected in parallel, so their final voltage will be same. We can say C1 and C2 are connected in parallel, Therefore final voltage across C1 and C2 will be same. Let us call this as V final, and we can easily find out this V final will be equal to charge final divided by C1 plus C2. Charge final we already know is our C1 times V naught divided by C1 plus C2. Now final energy stored. Final energy stored. Let us call this as U final. This will be our half, and we have this as our C equivalent multiplied by V final square. So we get our V U final will be equal to half C1 plus C2, and V final is our C1 V naught C1 plus C2 whole square. And we can just solve it a little bit. We get this as our half C1 plus C2. This gives us C1 square V naught square divided by C1 plus C2 whole square. The C1 C2 with the square cancel out, and we get this will be equal to our half C1 square V naught square divided by C1 plus C2. And we are supposed to find out the energy loss. So we can say loss in energy. That is our delta E will be equal to initial minus final energy. Initial energy is our half C1 V naught square minus half C1 square V naught square divided by C1 plus C2. And we can take half C1 V naught square as common. So this comes as 1 minus C1 upon C1 plus C2. And we can just solve it. This will be coming as half C1 V naught square. LCM will be equal to C1 plus C2. C1 cancels out, so this comes as C2. And we can just substitute the value. We know that our C1 is equal to C and C2 is equal to C by 2. Therefore, delta E will be equal to our half times C V naught square, and this comes as C divided by 2 C plus C by 2. And this will be equal to our half C V naught square. 2 will be per LCM. This comes as 2C divided by 2, and this comes as our 3C. And this 2 and 2, C and C cancel. So this will be equal to delta E will be equal to, this will be our 1 by 6 C V naught square. So this is the loss of energy, and option number 3 is correct. So here it's a little bit tricky, I think, because the solution is not justified actually. Okay, so let me do it in a different way, because it doesn't match. So let me sort it out again. Much more easier approach is using the conservation of energy. Conservation of energy. We are having a final energy is our at point at a distance of y. So this gives us a half m v square will be equal to, from the height of mgy plus, we are going to have a change in the energy of the electrostatic. Okay. And we are interested in finding out the electrostatic energy, and for electrostatic energy we know that initially the charge was at a distance of r, and finally the charge is at a distance of y, or the total distance of r plus y. So, and the charge on the sphere is capital Q, and the charge mass which drops is having a charge of Q. So we can find out our electrostatic energy, initial electrostatic energy. Initial means, let us suppose this is our A and this point is B. Initial electrostatic energy will be equal to our, at a distance of r, so this comes as k q multiplied by small q and divided by r, and this electrostatic energy at point, let us call this as VA. Now we can find out the final electrostatic energy. Final electrostatic energy, that will be our k q and at a distance of r plus y, and this is our VB. So therefore change in electrostatic energy will be equal to our VA minus VB. Sorry, not VA but UA. V is our potential, so this is our UA and UB. Similarly here also it will be UA minus UB. So we can take K Q multiplied by Q as common, and this will be coming as 1 upon R minus 1 upon R plus Y. Now we can just solve it. This will be coming as K Q and R into R plus Y will be our LCM. So this comes as our R plus Y minus R. So this comes as a, so this is our change in electrostatic energy. And we are going to substitute in equation number 1. So we can say from equation 1, we get half m v square is equal to mgy plus, this is our k q and we have y upon r times r plus y, and we can multiply it, so we get our v square is equal to, this is about 2 mg y divided by m plus, we get this as 2 k q times q upon m, and we have y upon r times r plus y. We can take this m and m cancel, we can take 2y as common, so we get this as a 2y will be equal to g plus, we have this is k we can write as 1 upon 4 pi epsilon naught, and we have this as q multiplied by small q, and this comes as our r plus y and mass m. So this is our v square. This approach is much better. Previously I'm not sure, I'm not able to find out where I made the mistake, but I messed up it big time. So my apology for that. So the conservation of energy is the approach with which we are going to get the same answer. Okay, just ignore this first part of the solution. So this is the correct one. So we get option 4 is correct. this completes finally the 15 question from the year 2020, and this was the part 1 for the, you can say, for the year 2020. Okay, we will try to cover the rest of the questions which are left from mains as well as advanced in the subsequent parts. Okay, so this completes the first part of year 2020 consisting of 15 questions. Thank you.